Okay, so it's a great pleasure to introduce the speaker, Markus Oberthaler. He recently carried out a series of fantastic experiments on using quantum simulator ultracold atom systems to explore inflation. Markus, please go ahead.
Yeah, thank you very much. Inflation is maybe I would be more careful. What we really did, and I would like to use this afternoon for introducing what I think is the legitimation that we say we have a quantum field simulator. And it's not only the latest results I will talk about, but also what we did in the last years. And it's in this context of we are not dealing with particles hopping from one side to the other, but we are in this continuum limit, not only in emotional degree of freedom, but also in internal degrees of freedom. Okay, and that's why in the following I would like to talk about three topics. I would like to use the first one to introduce a little bit more general perspective, also maybe initiating discussion what one can do in the future. This is not about this kind of metric engineering. And the last one is, I will talk about this a little bit longer, about what we did in implementing a system experimentally. They can study scalar quantum fields in curved space. The scalar quantum fields are non-interacting and massless. So the simplest things you can think of. And I think it's a start for something and not the end. Okay, so to put this, what I call quantum field simulator in context, this is what you typically see if you hear about quantum simulators in our field. And obviously you are a different community. So maybe you have seen this, but you immediately put it to the side. And this is naturally simulated or emulated by a quantum system with ultracold gases. If you put the atoms on a lattice, having them hopping around with internal degrees of freedom and interaction between the atoms. And this is well known and well developed, beautiful results on that. But condensed matter is the end of a long story. And if you look at the whole evolution of the universe, condensed matter starts about here. But there's lots of time where this is not the physics we are dealing with, but we're more dealing with fields at the end and interacting fields, and how out of these fields we get what we have at the end, namely our material. And it's not that we are going to simulate this universe. It will be inspired by certain questions raised in this kind of context, and a certain essence we can take out and then implement that in our cold gas systems. And finding interesting, I find interesting new perspectives, and not yet earth-shattering results, but perspectives, I would say. Okay, so if you want to simulate that, and you would take this kind of system, you might think, well, continuous in space is something you would like to have. That's easy, actually. You do one step less than the others. You just take the gas as you have it. Then we have internal degrees of freedom. And in order to reach here, the continuum limit, you would say, well, if I can count the atoms one by one, it's not yet continuous. So what we do is we take many of these atoms and then actually look in a volume where I have more than 1, 2, 3 particles, more in the sense of 100 particles. And then actually, if you have this kind of nice quantum field theoretical setting, it's also important that you have the way of kind of detecting the interesting quantum fields. And actually for that, it's advantageous to go to reduced dimensions. And the kind of metric engineering we did in 2D, the first step what we did was more into going in 1D. So actually you squeeze the whole system down to a one-dimensional situation, and that helps you, as I will show you, that you can detect the quantum field. Now, what is the quantum field here? You would say about the particles here are spin 1, so you would have 3 fundamental fields describing your system. But we are going to work with composite fields. The composite fields we can detect, but you can also describe them quantum mechanically. And how does this come about is, since we are not detecting single particles, they are anyway indistinguishable in this kind of settings. We're looking in a voxel. Okay, and this voxel has a certain volume, and in this volume there are about, as I said, 200 atoms with spin 1, for example. So now what's the field you would use for describing the system? a natural thing would be the order parameter namely magnetization. Yeah? Magnetization is a vector pointing in x, y, z direction, and it's a kind of an order parameter for the system. Since we are interested more in the quantum part, we would say, well, this order parameter here, f, is actually an operator. It fluctuates, and this is described by the operator, because it's built up by individual spins, making up this collective spin. So the order parameter, the mean, the order parameter, the fluctuations are something we are interested in. And that's what I call quantum field. Okay, so now if you have this kind of object and you want to detect this experimentally, it means you have to also not only look for the mean, but you also have to look for the fluctuations. Now, this is by itself extremely hard task, because you have a system which is embedded in the environment, it's fluctuating like this, the whole system going up and down, the vector is going this and that. But analyzing so one spot of this system and do their systematic measurement is very hard. It's also theoretically wise. So actually what you typically do is you ask about correlations. You ask about how does one spin correlated to the other spin, or one order parameter to the other order parameter. So yeah, talking about 2-point correlation functions. And that's essentially what we do. So essentially what we analyze is ensemble averages of 2-point correlators, or 3-point correlators, 4-point correlators. And there are many people in the audience who did do the same thing. But that's the way how we look at our experimental data. So now the question is, can we read out F operator? Well, operator definitely not, but expectation values of this operator spatially resolved. So now one tool we have developed over the last years is that we are not now interested in these kind of individual fields, so spin up, horizontal, spin down for the spin 1 condensate, but we are more interested in this kind of collective spin vector. And how we read this out is we use a trick, and this was actually developed by Philipp Kunkel. And we use the trick is that we expand our Hilbert space using additional degrees of freedom, which are empty initially. And this emptiness is actually essential. Yeah? So we have empty space, vacuum, so to speak, and we couple our system to the vacuum, and then measure actually afterwards all kind of outputs we can have, and these are classical probabilities. To be more concrete, what this is it's like in the spin degree of freedom in rubidium, that's the atom we are using in this experiment. F equals 1 is the spin 1 submanifold that we do the physics in, but we have F equals 2 there. So we can use that as a Hilbert space, which is empty initially, and we can couple this system, which we are interested in, into the bigger space, and then do projective measurements in this bigger Hilbert space. And out of this projective measurement, we get numbers out, and from these numbers, we can infer the observables in this subsystem. Now, it depends a little bit on this, how you map this up to the state and how you do the rotations or manipulation in the submanifolds. But what you can do is you can essentially have all three of these 8 generators read out in the experiment. That means locally we can read out expectation values of Sx, Sy, Sz at the same time, or Sx, Sy, Qy, Z. And you can take 3 combinations, and if it work a little bit harder on it, then we can implement all the 3 pairs, three together of your choice. Okay, so the simplest thing, what we did was taking X, Y, and Z and made a spin wave in the experiment. We implemented this kind of spin wave in the system. And what you read out at the end is locally not 3 densities, but you read out 8 densities at each spatial point. And out of these 8 densities, you can infer, since you know the unitary transformations you performed here, you can estimate what is the expectation of X, Y, and Z. It's important. It's not a single spin. It's always a collective spin of about 200 particles. And this gives you the expectation value spatially resolved. Okay, so now if you have this at hand, one can start asking questions. You have now a system which has a quantum field, which is a composite field, and you can read out this composite field. So now the question we asked or answered or addressed some time ago was inspired by a quantum field theoretical description by this kind of little bang. It's also connected to the universe experiment, which is done at CERN. But there, the name of the game is to investigate quark-gluon plasma. gluons and quarks are free. They are not bound. They're at a high density and high temperature. And this is produced by heavy ion collisions. Okay, and it's a very complicated behavior. You have this heavy ion collision producing initial energy density distribution, which then redistributes as hydrodynamic expansion and the difficult physics, hadronizing at the end. And then after about 10 to 22 seconds, everything is over. And then actually 15 orders of magnitude later, you look at what comes out of this kind of collision. And what you measure are hadronized particles, mesons and hadrons, and you measure their energy and their momentum. And out of this kind of detection, you want to infer, or you do infer, what was this kind of phase, what was the chemical freeze out, and maybe it was the hydrodynamic expansion before that. So in the context of this history of the universe, we are now at about 10 microseconds, in the order of 10 microseconds, that these CERN experiments are probing the physics. Okay, so now this is a very complicated high energy physics quantum proton dynamics problem. And all we have available is a spin-1 Bose gas. And how can you hope to contribute at all to this kind of question? Okay, so now one can ask about the very early phase of this after this collision, which is the high density. And that high density, we know that the strong interaction is weak. Right? So it's a question of kind of what Q you look at your system running coupling means actually a weakly coupling Bose gas of gluons at the very beginning. Okay, and the description here was now, can one understand mathematically how this kind of initial distribution develops into something which might look thermal, and then all this other stuff happens when you get strongly interacting and this hydrodynamic flows. This was actually not done with chromodynamics. It was done with a model, and that's actually always what I'm saying. We are not doing the real world physics. We are trying to implement models, mathematical models, which are well defined. And the model here is the ON model. So essentially, it's this kind of, this is an action. Essentially, what I take out of this, and I'm not an expert in actions, but I try to learn this language here. So here you have the kinetic energy. This is a relativistic theory. But here you have the interactions. And then the funny thing is that all these fields, A, B, and this runs over all fields you have, they all interact the same. This is special. If you have this model, ON model, you can make predictions, and this looks like this. Don't ask me details about what this really means here, but it makes predictions about dynamics. Okay, and in the n to infinity limit, you have analytical solutions. One important part is that objects which appear here naturally have 4 vertices, i.e., 4 fields coming together, which become explicitly time dependent. So this is all about time dependent. You smash the thing, you have time dependent, and you ask what happens in time. So what came out of this kind of calculation, and Jürgen Berger's is here the pioneer, what came out of this calculation was that the dynamics can develop in something simple. Namely, it has this kind of initial situation where you're far from equilibrium, and then it develops into a time dependence which is universal in the sense that you need only few numbers to describe it. How this works is essentially that you look at the 2-point correlators. As I said, that's the only thing we do experimentally, also theory-wise. You look at the 2-point correlators, and what you find is these 2-point correlators, if you plot it in momentum space, so you get the kind of length scale here. Here is long wavelength, here is short wavelength. These 2-point correlators develop a very simple shape, and this shape doesn't change in time. All what happens in time is that it shifts to the left. So structures get larger and larger and larger. Actually, not structures in the sense of patterns. It's fluctuations. So the fluctuation on small scale go to fluctuations on large scales. And this does it in a peculiar manner, namely in a kind of exponent t to a certain exponent beta. But universality means this whole dynamics you can describe in a very simple way, that this structure factor, i.e. the Fourier transform of 2-point correlators, develop with a universal function, might be hard to calculate, it's something what the simulator will give you maybe, and 2 exponents. One exponent which rescales the length scale, and one exponent which rescales the amplitude. That's a kind of prediction. And the prediction for the ON model, and it might be more general, it might be also for other systems, are happening. Okay, so now this is something we did experimentally, and we have no Big Bang, but we can produce a situation which is definitely far from equilibrium. And it's actually starting here in an easy plane ferromagnetic phase, which you would then describe as having a free energy, which is this champagne bottle bottom. But we start with an initial state, which is here at the maximum. And this state is definitely far from equilibrium, because equilibrium would be somewhere here, and you have a symmetry broken state. So if you measure it down here, you would find a polarization in random directions, but it would be correlated along your extended system. Now, having this readout available, you can directly look at the dynamics of these fields. Now, these are your fields of interest, Fx and Fy. This is because we are in a special phase here. And if you do this, you see actually what happens. This is this kind of equivalent of this kind of smashing of heavy ions during this quantum quench. And you see how the system develops in time, spreading out over the whole phase space. But then after a certain time of 14 seconds or 20 seconds, settles down to this ring. So it looks like as if it settles here in this ring, and then after 42 seconds, it's actually nicely settled. And the question now is this thermal or not thermal? And this kind of, if you look at this kind of occupation numbers, or like say, what kind of probabilities you have to have a certain moment, a certain spin, you don't know, right? You just know it might be settled to a thermal equilibrium, but you don't know if you look at it this way. But we have more information as we have real space images. So we really get this whole picture out of ensemble averages of many realizations. And each realization has a certain image. Yeah? You see a certain kind of configuration, field configuration, which has certain connections between this side and that side. And this is one realization, one field configuration drawn in here in this kind of picture here. Now, out of these field configurations, you can do now the correlation functions. Okay, so you do the correlation functions, 2-point or 4-point, and then you can do the Fourier transform and then ask, can one see what has been predicted for the ON model? And the interesting thing was that indeed you can see that the structure factor has develops in time. And if we rescale the structure factor, actually you get this kind of collapse on one function. There are certain exponents, alpha and beta, of 0.45 in this case. Now, there was a back-to-back work by Jörg Schmidtmeyer doing this with one-dimensional single component Bose gases. We also found other exponents, which is hinting to the direction that is not only one, but there are maybe many. And how to classify that is definitely something which is a task we still have to do. But a quantum simulator, a quantum field simulator, might give here some input. And Thierry Cemaki gave recently a talk, I've heard him, and he said it's not a quantum field simulator, it's more maybe a quantum stimulator. Because at the end of the day, these results are no answers. They are one result, and then understanding it is, I think, has to be done by theory, and reducing it to equations, one can maybe then say this is what one means understanding. Okay, so now what can this simulator give you more? And this is a little bit in the spirit of what can we do after what I've told you at the end. Yeah, what are the next steps? And one thing is that you might wonder, can one derive from observing this kind of phenomenon something about the dynamics or the Hamiltonian? And the Hamiltonian by itself is not the right language here. It's maybe better to take this quantum effective action, because we measure correlation function. The quantum effective action is generating functional for correlation functions. So essentially, it's a different way of sorting. I'm used to density matrices. Quantum field theory people, as many of you, are more used to quantum effective actions, which are actually all possible observables you can do experimentally. And it's much more natural to connect to what we have done here in this experiment, because it's about correlation functions. So these are expectation values of correlation functions. Now, this quantum effective action, you can try to expand in a kind of Taylor expansion. And then you have these kind of components. And that's what we have seen before. There was this gamma T, alpha, beta, gamma, delta, which was this object with 4 fields here, which was entering the prediction for the ON model and this universal dynamics. The question is, can we somehow extract this experimentally? And realizing that essentially this is the general functional for correlation functions, one might think, yes, if you have the 4-point correlation function, you can back translate it into these gammas. Okay? Essentially, what it says is the 4-point correlation function, if it would be simply given by product of 2-point correlators, well, then it would be the solution, and we are done. But there's more to it. There might be also a multiplication of these correlation functions times an object. This is a 4-dimensional object, and it's known as one-particle irreducible 4-vertex. This is just a way of reformulating and reshuffling the information you had already here. Yeah? But it gives you a kind of more intuitive understanding, maybe what's going on. Okay, this is something we have done. And what we found out is, actually by doing this 4-point correlation, what you find out is that indeed this high-dimensional space, you get structure, you get naturally out that you have momentum conservation. These are now 4, P1, P2 is going in, and P3 and P4 is coming out. I'm not going into details here. It's more about that you can look at these kind of inputs of these gammas as a result. And what you find is that essentially these gammas depend on P. And if you interpret this as interactions, what you find is that interactions depend on the length scale. Here, the long length scale interacts stronger than the short wavelengths, i.e. high momentous, interact stronger than the long wavelengths ones. That is a result. This is something what comes out. Now, it's a theory question. Does it have to look, why does it look like this? And does it look like this? Why does it come from? It's all emergent out of these interactions. And so far, there is no prediction why it looks like this. So this is a challenge for people, maybe in the audience, to figure out why this looks like this. That I would like to move on to the original topic. Okay, so we have quantum fields. We typically don't look at fundamental fields of our experiment, which are the atomic fields, but we look for composite fields. And that's what we are also going to do now in the following, when we talk about this quantum field simulator for dynamics in curved spacetime, which was the title of the talk. So this was a result of a wonderful team of people working experimentally with a potassium 2-dimensional system and with a theory collaboration with Stefan Flöchinger, who was in Heidelberg and now is in Jena, moved to Jena beginning of this year. And the whole thing was initiated by our excellence cluster structures, where we said we want to do quantum dynamics with horizons. And how quantum it is, we can discuss, and I think there's room for improvement to show more quantum in the future. Okay, so what we not do? What we not do is cosmology. So if you have the metric and you ask how does the metric evolve in time, then there are Einstein's field equation tell you something about how they should develop in time. And it's a complicated thing, and don't ask me, you are the experts, you can tell me more than I can tell you. But at the end of the day, you would get out of this equation the metric, okay? So now, if one assumes the cosmological principle that this should be homogeneous and isotropic, the metric already is constrained massively. So it's not all possible metrics you need to look at, but constrained. Now, all I'm doing in the following is 2-dimensional physics, because it's the only thing we can do now at the moment. So we do a further reduction, and in 2D, or generally, this kind of reduction of the structure of the metric because of homogeneous and isotropic assumption is the Friedmann-Lemaitre-Robertson-Walker metric, which has this kind of form. Okay, this is a line element, and for me, as a beginner in this field, I look at this, I know T and U and phi, but there are 2 parameters entering additionally, which is kappa, which is the curvature, and A, which is a scale factor. So at the end of the day, if I want to do with this assumption an implementation experiment of a general metric, I have to have control over the scale factor as well as of the curvature. Okay? But then I could be happy, or I am happy, and then I've done something relevant, I hope. Okay, so now the question is, how does one implement that? Okay, so if you look at this metric and it's kind of something, since it's 2D, having curved space, 2D curved space embedded in 3D, one can visualize it. Okay, so you have a hyperbolic plane in real space, And if you would ask what's the geodesics, i.e. the shortest connection between 2 points, then this would be following this kind of metric. Now this infinite space, and infinite space in a lab is hard to implement. But one thing one can do is one can map this infinite space onto finite space. It's like Poincaré mapping. We can map this kind of infinite space, since this is the tangent here is a linear tangent at the infinity. You can map this infinite space onto this finite disk. Okay, which sounds good because finite system is what we have experimentally. But if you look then at the finite disk, then suddenly the metric on the finite disk is strange because the scale factor becomes space dependent. Okay, so now if you have a scale factor which is space dependent in this very peculiar manner, then you would have this kind of curved space implemented experimentally. Okay, so essentially what I draw here are the circles of equal distance. And I can imagine if I'm at the edge here of this hyperbolic space and I do my length definition, like a switch on the lamp, and after a certain proper time, I measure what is the radius. Then this radius, if I project it down to my plane, gets distorted and gets smaller and gets strongly distorted. Okay, but nevertheless, if I can do this here, then I'm in business. Now, this kind of metric is interesting because it's also in our logo of our structure logo, which is actually showing all the connections within our group. And this is the hyperbolic geometry, and it's the same thing here. This essentially is hyperbolic geometry. That means the circumference here is infinitely long, and that's because the ruler gets infinitely small. Okay, and length is measured through how many times do I have the ruler. Okay, so now the question is still, one can do this. Can one generate a real experimental situation where the ruler, the natural ruler in the system, changes its function of position, and it gets smaller and smaller as you go to the edge. And here now actually our system comes into play. So what we have is a two-dimensional Bose gas of potassium-39. Realized here, you see the red spot here in the middle. This is the gas, and then we confine this in two-dimensional optical traps to have a two-dimensional gas, and that this is a density distribution we measure. Okay, so you have high density in the middle, low density at the edge, and that comes from the fact that we trap this gas in a harmonic trap. Okay, so now, since I talked about quantum field simulators already on an effective level, we have to ask what kind of fields are we going to look at? And we're going to look at the phononic field. So phonons are collective excitations of this Bose gas. The individual particles are gone. You just look at sound waves of the system. And obviously, this has to be a limit, right? It is looking at just the collective behavior means I'm not looking at individual particles. So that limits our experiment to a certain length scale. We cannot look at infinitely small length, or a small length scale, because then you would see that they're particles. Okay, and the natural length scale here is the healing length. So we have to look at physics larger than the healing length. Okay, and in this limit, they're going to work. And then there, the objects describing the physics are phonons. Okay, propagating with the speed of sound. Okay, if I have now the system and I would like to find out the natural ruler, what's the natural ruler? Well, it's the velocity times the proper time. Okay, so if I do this, here I make it a kind of distortion and avert a certain time and ask where does this distortion go to, then it will expand. It will expand with the speed of sound and defines a length scale. Okay, if I do the same experiment at the edge and ask, now, how far do I get there? Then you will find, well, okay, out here, you are slow, you don't get as far, and if you go further in the middle, you get faster. So essentially what you get is now a distortion of your ring. Essentially, it means, like if I make it very small, I would see the ring is smaller than before, and that means my ruler gets smaller and smaller as I go to the edge. That's just the sound velocity goes down to 0. Now, in this metric we have seen before, this has to go down with a peculiar manner, and it has to be a quadratic plus a warp power power law falling down. This is not what we have experimentally. So essentially, we are limited to about half, let's call Thomas Fermi radius, half the Thomas Fermi radius, but this is a good approximation. Okay, so now where do I see now here the hyperbolic geometry? Well, if you do this kind of Escher picture in the back, which actually I didn't mention before because Escher was an expert in doing hyperbolic geometry, then you see the eyes of these birds or whatever this is defined here a circle. And if you go outside here, you see they again define the circle. Essentially, this shows you that this kind of phonons behave like this hyperbolic geometry in an approximation to a certain size. Okay, and with that, we can, in this size, we can implement curved spacetime. Okay, so now we have to ask if this is the metric which defines the connection between space and time, what is the field we are acting on? And I already told you the field was defining the metric, but the field is also what we are interested in. These are the phonons. Okay, and that means we write down the field as something like the background field, which is, if you square that, that's the background density of our condensate, plus some excitations on top. These are typically, in this very peculiar manner, it's the orthogonal representation of phonons with a real part and imaginary part. Okay, and these would be small distortions on top of this background field. And now if you take this seriously, and that's what Stefan Flöchinger did, you take the imaginary part of this phononic field, he derived that essentially this imaginary part follows this kind of action. And this action has actually here now a metric G mu nu and is massless as well as non-interacting. Okay, so essentially it's just now a field where the metric is under our control because we can change the curvature, i.e. we can change the density distribution, and we can change the scale factor because we can change the interaction between the particles, i.e. the stiffness of our system. So the effective field is now the imaginary part of the phononic field. At the end of the day, the question is now, can we really observe phi experimentally? Or actually better, can we observe phi star, i.e. the phi at position r and phi at position r prime, and do there the correlations. And it turns out for us, it's much more natural to go for the conjugate field. So phi dot, at different positions we can correlate, as I will show in the following. Okay, before going to that, one can ask, can one show the metric in a simple way? And the simplest way of showing a metric is throwing a particle or taking a light bulb and look at the straight line, the shortest connection between 2 points. So in our case, it would be a coherent state of phonons. A coherent state of phonon you can generate by making just a small dip in the condensate. This is now already an image where we bracket the background because we're only interested in a small modulation on top of the background. Okay, so if you would do this here, you make a small distortion and you ask what happens in time, then you would expect that this thing would expand, but it should expand corresponding to the metric you impose. And that's what you see. Essentially, this goes out as a ring and spreads out. Well, it's hard to tell, it's a ring or should it be an ellipse? Well, it should be an ellipse. It should be not a circle because the metric here should change as a function of distance. The distance measure should change as a function of distance. So you would expect it should be not a circle. Now you can do this, if you do this here in a cut here through here, and I show this here, this is the main image, direct density images, but here you take the difference, so take the background, weigh the background so you see better the small modulation, and you run around this kind of direction, you run around the geodesics, and then you can look at how does this kind of wave packet expand on this geodesics. And that's what you see here, that it expands, actually propagates, and if you look at the minima, you find out the minima propagate along this kind of lines. The petrol line is the kind of simple naive assumption of this curved metric with this hyperbolic geometry. And the gray line is really what you have in your real experimental system. Essentially, what you see is the system is curved. You also see the limitations. It's not that it can go to the full edge. and explore all this kind of nice structure of hyperbolic space experimentally, you can just grasp here the edge and see that there is curvature present for this case. Now, if you would look at just this circle, and you can do this in a circle and analyze the minima, then it looks like this. And if you look at this, you see that it's obviously distorted. These are rings here. And you see that the minima are not going along a ring. Actually, this is an example. This one is the outer ring, and here it changes to the inner ring. You clearly see the distortion. And this is exactly what you would get, because you have here the ruler is not same over the whole system. It changes as you go out. But if you now would go here in this kind of hyperbolic plane, and you would look in there, you would have a circle expanding. Okay, and this you can do is a transformation. You can do the transformation. And if you do this, then essentially you see indeed yes, this kind of wave packet propagates outwards, and it's along a ring, concentric rings propagating out with the same distance. Here is a transformation included, where actually you would expect that this actually grows linearly with the time. Okay, so this is now a way of how we show that we have implemented curved space or space-time, curved metric. And having this done, and having this kind of picture that essentially making negative curved space by having a ruler which gets smaller as you go out to the rim, you might wonder if you can do also like a positively curved space. And then if you look at the mapping here, you find out that what you have to do is you have to make a system where the ruler actually gets longer as you go out. Okay. Now, translated into sound velocity, what it means is you have to have a system where the sound velocity is larger at the rim than in the middle. It is not the most natural situation for a gas in any trap. But if you take like light fields and you can configure your trap, you can make a trap in such a way that actually the density is larger at the rim and minimum in the middle. It's not going to zero, there is a solar background, but it has kind of a density which is spatial dependent in this manner that you kind of have this curved space implemented. Now the wave packet in this kind of situation propagates differently. It propagates fully distorted. There's no ring anymore. It actually makes a line. And this is actually, it would be a ring on this curved space, but since you have this peculiar mapping, you get this distorted evolution of the wave packet as you see here. Okay, so in this respect, now what you can do is you can implement negatively and positively curved space, and you can also implement flat space. And now with this kind of new system, you might have a new question, which is not cosmologically motivated, but potentially motivated by the possibilities. What happens if you have curved space, which is negative, and you make a change adiabatic, most likely impossible adiabatic, but you make a change from negatively curved space to positively curved space? What kind of excitations would you get? It's something one can ask in the future. Okay, so with that, one has to ask the next question. I said, if we have this kind of space, you also would like, or this kind of FLRW metric, you would like to have situations you also can say the scale factor in time. So at the moment we changed it in space, but we had to do this because we mapped it onto this peculiar mapping. Now the question is, can we change the scale factor? So an expanding system. And this is obviously an expanding system plotted here. And the question is, take a BEC and expand it. Yes, you would get this. But can you do it also without moving the BEC? Just keeping the gas constant, can you expand it? And essentially what you have to do is you have to change the ruler. So this is the same situation. The system is kind of constant in size, but the ruler changes in time. And thus now the extension here is 10 times the ruler. Same thing here, as here says the ruler constant, but the system gets 10 times bigger. So this is equivalent in 2D. How to do this? Well, all we have to do is we have to change our ruler. And I showed you already the sound velocity is our natural ruler. And how we can change the sound velocity globally now, not locally, globally, is by making the system less stiff. Okay, and the stiffness of this gas is nicely adjustable because we have control over the microscopic degrees of freedom, and that is the interaction between the atoms. So if they have a weakly interacting, this is soft, the system sound velocity is low. If they are stiff, they are stronger interacting, then the sound velocity is fast and is stiffer. So we can change this, and we can change this in a very controlled manner. This is done by flashbulb resonances by many people also in the audience. Okay, so at the end of the day, one can ask, how does this scattering length A connect to the scaling factor A, which is unfortunate. So that's an S for scattering. And there is a direct connection. If you make a scattering length small, you increase the scaling factor, but radically. Okay, so essentially now we can directly translate. This is under full control. And if you have this translation, we can change the scale factor in time as almost at free will. Now, the choice of changing it was done that we do a power law. And this comes motivated again from the cosmological part. If you have this FLRW metric and you ask what kind of scale factors can you predict, then you can ask what kind of equation of state you can assume for your system. And if you have this in this manner, then you would say, well, you would expect a power law dependence of the scale factor. Since we have no dynamics, we can imprint this in our system. We actually looked at scale factors changing with the power law and changed this gamma. The gamma not now because it's two-dimensional. If it's matter or light or photon-dominated or radiation-dominated universe, doesn't make much sense. So we choose gammas to what we for kind of somehow arbitrary, but the most natural one is gamma equals 1. And then you do one smaller and one larger. So one decelerating and one accelerating universe. And universe is not what I should say. It's a kind of the metric what we change. Okay, so theoretical wise, you would describe this in a very natural way, and more better experts in the audience than I am. But essentially, it's relatively straightforward to calculate what should happen in this approximation that we only have for Grubov modes. Okay, so we have a region 1, which is the initial condition. We have the region 2, where we change the scaling factor. But then we have also region 3, where actually you stop your whole dynamics and you just wait. And we're going to use this kind of waiting time for analysis and extracting information about what you get out after the ramp. So what we calculate then, the most natural thing is, for example, this correlation of the phi, but also of the conjugate phi dot. And this correlation function, interestingly enough, and it's important, does not depend on the variables u and phi, which is microscopic at the positions u and phi you have in your system. It only depends on the distance between those 2 points in the appropriate metric. Yeah. So at the end of the day, we have this correlation function which depends only on distance between points, not on the absolute position in our experiment. More importantly, this kind of phi dot directly translates in an observable, which we call contrast, density contrast, which is actually a density minus the background density. So actually a fluctuation on top of the density. But the important part here is my naive expectation would have been we take the density difference and normalize it to the mean density. That's a natural thing we do. If you look for quantum correlations, that's a natural kind of reference we take. But here it's opposite. It's not like this. You have to multiply it with the square root of NR in order to make the connection to phi dot. Okay, so this is actually something which came out of really dealing it theoretically properly, knowing what kind of correlations you have to look at in order to be able to compare it with theoretical predictions. Okay, so we have to take the square root of the density times the density difference. And at the end, what we find out is, well, the correlation functions in density contrast is now observables. Yeah, these are observables we can do experimentally. They are connected via a factor with the correlation function calculated theoretically. And this lambda f, I'm sorry about the notation here. This is the final interaction. This is final scattering length, AS final. And theory people called it lambda. So this is the final interaction strength. Okay. So at the end of the day, now what we can do is we can extract this experimentally. This is measurable, observable, and compare it with theoretical predictions. Now, as I said, we have to change the scattering length. And this is a result what you get if you do, for example, a gamma. Remember, this is a scaling factor, which is exponent square root. So it's square root of t. That means we have a decelerating unit, a decelerating metric. And this is what you see here is a density. That's a start, it's initial condition. And after the ramp, it looks like this. This is a density as you measure it in the experiment. Now, as I said, this is not the observable you want to compare with the theory. You want to compare it with the contrast, and that's plotted here. So this is the initial condition. This is kind of quantum plus thermal noise of your initial state. And if you do the ramp, this translates into this kind of noise, okay, with this ramp. And you see already there with player I, the noise changes. Yeah? It gets structure, it gets larger structure than here. And the good thing about this system is you can do this now repeatedly and actually extract the correlation function over an ensemble average. Okay. So if you do this, then you start doing this for the initial condition. If you do this for an initial condition, and you take all kind of differences, so here is the difference plotted and the number, and you take all possible differences in the experiment. It's not kind of correlated with the middle and the rim. You just take differences appropriately, and then for different differences, you get these correlations. Okay, the statistic gets worse as you go for quicker distances, but this is the correlation function for the initial condition. If you do this after the ramp, you get this kind of result. There's an obvious signal that they get anti-correlation plus correlations at a certain length scale for a certain ramp. Okay. Now this is a representation of these fluctuations. Now it turned out that essentially for us, in order to measure these amplitudes here, actually better to do the following. So we have this ramp. We produce these kind of excitations. They have no spatial correlations. They are somewhere in the system. And then we let the system evolve under no expansion, under a kind of constant metric. Okay, and if you do this, each of these kind of excitations will kind of spread out and does this with the speed of sound. Okay, and this thing we analyze now as a function of holding time. So as this kind of spreads out, we look at the correlations and analyze these correlations. So this looks now in real space like this. So here you have time after the ramp. So as you go along after the ramp, you have first these correlations. And as you go along in time without expansion, just a natural kind of metric, it spreads out with the speed of sound. Okay, and what you see here are two different ramps that do a fast kind of change and a slower change. Okay, and this kind of expansion here, these are Sakharov oscillations in real space. This is actually not a typical thing you look at them. But it turns out that this is very advantageous for our analysis. So now if you do this, go into this momentum space, which is a more natural thing. So we go for length scales in the system for different ramps, then it looks like this. So for different decelerating expansion, a uniform expansion, and an accelerated expansion, you get this kind of structure factors, i.e. the Fourier transform of this correlation function as a function of time. And this might not tell you much, but you see at least there's something produced. Yeah, there's the black one is the initial condition, and you produce everywhere at all cases, you produce excitations. Interesting is, if you look at this kind of length scale here, and you look at it not in this way of different time plotted structures factors, but look at 1K, how it develops in time, then you get the Sakharov oscillations. So each K oscillates in time with a certain frequency. The frequency is actually given by the free evolution of these Bogoliubov modes in this non-expanding situation. And these oscillations you can measure nicely in experiments. So as you go up this K, you see the oscillation frequency goes up as it should be because they are phonones. Higher K have a faster frequency. Okay, and you can do this for different ramps. Decelerated universe, constantly expanding universe, accelerated universe. Sorry, universe I should not say. It's kind of the metric. Yeah. Okay, so now if you do this analysis, it's a very interesting situation that now actually the population of each of these modes is not taken out by after just directly looking at the lamp after the ramp. What we do is you look at the amplitude of the oscillations. Okay, the amplitude of the oscillations, since the perturbation numbers do not change anymore, they are given by the ramp, they are produced within the ramp, and then you have it. It's just evolving phase. You can take out of the amplitude, you can read out what was the perturbation number at the end of the ramp. And that's what you get out. For the different ramps, you find out, well, there's certain low Ks are highly occupied and high Ks are less occupied. And if you zoom in here, you see actually a structure that there is a certain bump for different ramps. Especially interesting is the ramp gamma equals 1, which is actually the most boring one. It's a uniformly expanding universe. metric, sorry. Okay. Now this is by itself nice, but what was much more interesting is if you do this kind of analysis and you have occupation numbers, you can also ask about phases. You produce these kind of excitations, there might be certain phase relations, and that actually can read out by looking at these oscillations and how they oscillate in time. And here you see actually this goes up and down, and here actually changes, the phase changes in time as you go along. And if you analyze this in K-space, you find that the phase actually makes a jump. But experimentally, you never know if it's jump. But what you saw experimentally, the phase increases, and then actually it started again and increased. And the solid line here is a theory prediction. Okay, this is a theory prediction by the thing I showed you before, by just doing the standard, just inverted commas, standard Bogoliubov treatment and calculating this observable, which is not the typical observable you do. So now actually this was very surprising that this happens, but because what it means is if this is a jump and this is a real zero, it means if you expand your space uniformly, there are certain momentas which are in vacuum again. They start in vacuum, they end up in vacuum. In between, well, you might ask what happens if I stop the ramp in between? Well, you will find some occupation number there if you stop it, but if you don't stop it, it ends up in vacuum. And that's very interesting, I find. And it's a result which came out of this kind of quantum stimulator, because this was at least not looked at by the colleagues of mine working in this field. So phase jump is indicative for zero. And actually then afterwards, also inspired by the referees, they asked if there's some finding, one should also have an explanation. And it turns out actually one can make an analytical prediction for these phase jumps by mapping the whole problem to a scattering problem. And essentially what this is kind of transmission zeros or transmission ones actually in a scattering problem of a one-dimensional scattering potential. These are details I cannot explain you better than what I did now. This was done by Stefan Flöchinger, and we are at the moment trying to summarize this in a more profound way that is readable for everybody. So this is actually a result of the quantum stimulator or a quantum field simulator, if you want. And with that, I'm at the end. I didn't talk about things which you typically do, namely detection of entanglement, but these kind of tools we have available, they can also try to apply for this kind of changing of metrics, and then actually you would really have also a quantum result of the experiment. So far, we need quantum theory to predict what we see, and with that, maybe it is a quantum field simulator, but at the end, I would say it's a nice experiment showing that metric is something under a certain level of control now in the experiment. And with that, thank you for your attention.
Thank you, Markus, for your wonderful talk.